I will deliver a lecture on thermodynamic and kinetic aspects of metal complexes. This unit covers B.Sc third year inorganic chemistry paper first. This unit covers introduction, stability of metal complexes, stepwise formation constant, relationship between stability constant B9 and K1, K2 and so on up to Kn. Kinetic versus thermodynamic stability. Next topic is here, factor affecting the stability of metal complexes. As you know, almost inorganic reactions are ionic reactions and they proceed very fastly. But in case of complexes, somewhat the reactions are quite slow, and therefore we can determine their rate of reactions and velocity of reactions. Here there are two types of stability of complexes, that is thermodynamic stability and kinetic stability. The interaction between a hydrated metal ion and a ligand to form a metal complex can be regarded as Lewis acid and Lewis base, or we can say Lewis acid Lewis base formation form complex. Most of the metal ion complexes are quite stable. However, they dissociate in a slight extent in aqueous solution to maintain an equilibrium with central ion and ligand. The tendency of the complex to dissociate into metal ion and ligand. Thus, the stability of complexes will be given by the relative tendencies of two processes, that is association of metal ion and the ligand to form complex, dissociation of the complex to give back to metal ion and ligand. Means this is a reversible reaction. You find here stability complex in solution. For example, we are taking example of this AgNH3 whole twice Cl. In aqueous solution, it decomposes into AgNH3 whole twice, which is taken in square bracket. It is one species, and this is chloride ion. These chloride ions are splitted or detached very easily, and we can say here this is primary dissociation. In this case, we see AgNH3 whole twice in this complex ion again dissociate into Ag ion and NH3 molecules. These are in fact in equilibrium conditions and dissociate very less amount. This also called secondary dissociation. This dissociation, in fact primary and secondary dissociation is the outer and inner sphere of complex compounds differ greatly in their stability. The species in the outer sphere are bonded to the complex ion mainly by electrostatic forces, that is ionic bonding there, and are easily detached in an aqueous solution. This type of dissociation is called primary dissociation, as we already discussed earlier. The ligand in the inner sphere are much more strongly bonded to the central metal atom and are detached only a small degree. The reversible decomposition of the inner sphere of a complex compound is known as secondary dissociation. Secondary dissociation is characterized by the existence of equilibrium between the complex ion and ligand. As in earlier slide we see here, that is AgNH3 whole twice plus positive charge, it is dissociating in Ag ion and NH3 ions, and this dissociation is very feeble, that is in less amount. Therefore, the ligand in the inner sphere are much more strongly bonded to central metal ion or atom and are detached only a small degree. The reversible decomposition of the inner sphere of a complex is known as secondary dissociation. The secondary dissociation is characterized by the existence of equilibrium between the complex ion and ligand. The above equation 2 in previous slide, this is equation number 2. Like dissociation, any weak electrolyte and therefore obeys the law of mass action and can be characterized by the relevant equilibrium constant. That constant we can define the equilibrium constant, that is Kd, or dissociation constant, given by Kd is equal to active mass of Ag plus ion, NH3 molecules, and these are product and these are reactant. These are the product and this is one of the reactant. Kd dissociation constant of complex ion, we can also find out its stability. Stability is the reciprocal of this 1 upon Kd. That is again this AgNH3 whole twice ion and divided by active mass of Ag plus ion and NH3 molecules, we get the stability of constant value. Smaller the value of Kd, that is dissociation constant, greater will be the stability of complex. Thus the reciprocal of the dissociation constant is called stability constant of the complex. In the preferable, it is preferable practice to use the reciprocal of dissociation constant and called stability constant to characterize the stability of complex compound. Next, stability of metal complexes. In fact, there are mainly two types of stability of as applied to complexes. Number one, thermodynamic stability. It is measure of the extent to which the complex will form the transformed into another species when the system has reached in equilibrium. On the basis of this, Bleeds in 1927 has divided the complex into stable complexes and unstable complexes. For the thermodynamic stability, the requirement for there are if constant K is greater than 1 and G, that is free energy change, is less than 0, then compound will be more stable. Or if free energy can say that is should be in negative, or K should be greater than 1, means the compound is quite stable, or rather than unstable, it is stable. This means that the product are more stable, just as told to you reactant. That is delta G is equal to minus RT K, that is value this is called formation constant, and that is the formation constant is represented by the bond energy, and its stability also reflects its formation constant. Then next type of stability is kinetic stability. Kinetic stability refer to the rate of reaction. Metal complexes that undergo substitution reactions very slowly or do not proceed at all said to be inert. Metal complexes that undergo substitution reactions very quickly are said to be labile. For example, the complex CONH3 whole 6 hexamine cobalt plus 3 ions remain stable for a long time in acidic medium, which indicate its inertness or inactive. However, this complex is thermodynamically unstable as it has very large equilibrium constant, that is K is equal to 10 to the power 25. For the reaction, that CONH3 whole 6 plus 3 ion plus 6 H2O in aqueous, the ligand NH3 are replaced by water molecule and it form hexa aqua cobalt third ion. Constant is that is given constant is 25. This indicates that CONH3 whole 6 is thermodynamically unstable in acidic medium, but it is kinetically inert. Next example, nickel plus 4CN, it is forming tetracyanonickelate second ion, where the stability constant beta is near about 10 to the power 22. It indicates that the overall formation constant of the reaction is 10 to the power 22. This indicates that complex thermodynamically is very stable. However, the rate of exchange of cyanide ligand with CN14 is very fast. Therefore, kinetically the complex is labile. Means these ligands, in fact these ligands are exchanging and coming inside also, but here we have taken the isotope of carbon 14, and on behalf of this we have observed the exchanging of these ligands. And here you see nickel a carbon 12 CN3 and this is carbon 14 CN. Therefore, the complex nickel CN4 2 negative ion is thermodynamically stable but kinetically is labile. Similarly, we can also explain the relationship between, therefore, higher the value of stability constant of complex and greater will be its stability. Stability of metal complex. Just we already discussed these things. Stepwise stability constant. Overall constant and stepwise constant. Overall constant means reaction is proceeding in one step or reaction is in completion. But in fact, in complexes, the reactions takes place stepwise. Means the interaction between metal ion and ligand takes place slowly, and one by one ligand is interact with metal ion. Therefore, we can calculate its stepwise stability constant. Most of the metal complex readily reach of some of equilibrium in reaction in solution, depending of the nature of the ligands attached to the metal ion and the ligand concentration in the surrounding solution. This is expressed qualitatively by the formation constant of the form, that is metal ion plus ligand, it form metal ligand complex, where the constant K is, we can find out its active mass of complex ml divided by active mass of metal and into active mass of this ligand. We suppose next ligand is attaching to previous one, ml, that is metal ligand complex plus L, it form ml2, or its constant will be K2, active mass of M metal ligand 2 divided by ml into active mass of L, or we can say more than 2 or 3, you can say that ml n minus 1 plus L is equal to m active mass m L ligands, and its stability constant Kn will be ml n and divided by this ligand. The equilibrium constant K1, K2 or up to Kn are called stepwise formation constant or stepwise stability constants. The under mentioned steps are and equilibrium constant fully expressed in formation of complex, say that is metal and ligand forming this complex, and here stability constant, that is beta 1. Similarly, next step, when again next ligand is entering to attaching to this metal ion form in this way, and at the end metal ion and ligands form this compound, and the value of formation constant, that is beta n, will be this one. The equilibrium constant beta 1, beta 2 or up to beta n are called as overall or cumulative, means total formation constant or overall stability constants. Therefore, we can say that the stepwise constant and overall constant, if we calculate, the value will be same. The higher value of the stability constant of a complex ion, greater will be its stability. The overall stability constants are also expressed log 10 beta is equal to log 10 K1 plus log 10 K2 plus so on and log 10 Kn. Means the total of these value will be overall constant, that is log 10 beta. Log beta is a measure of stability constant. In general, a complex is regarded a stable if its log value is more than 8. For example, in the formation of complex, an aqueous solution of K2PtCl4, that is potassium tetrachloroplatinate second, contains in different proportions and all the complexes participating in the following equilibrium. This is one of the very interesting example. Say that is this complex ion PtCl4. In fact, when react in a medium, that is aqueous medium or with water, this water in fact replace one by one chlorine atom from inside of this complex. You see here, that is PtCl3 H2O, and one chloride atom is replaced from this complex. Here charge is 2 negative, here charge is 1 negative, means this PtCl4 is more negative than this one. In next step, PtCl3 H2O plus H2O, it forms PtCl2 2 H2O molecules, 2 H2O whole twice, and here it is becoming neutral. Here charge is negative, but here is neutral, and again another chloride atom is replacing from this complex. In next step, this PtCl2 H2O, in fact there is no charge at all, and again reacting with water molecule, this water molecule is coming inside, while one chloride ion is replacing this way, and here it is becoming a positive charge. Here was negative charge, here is becoming positive charge, and again chloride ions are replacing. In next step, you see PtCl H2O whole thrice in a square bracket plus charge, and again H2O. Here PtH2O whole 4, the whole molecule become positive charge plus 2, and again chloride atom anion is replacing from inner side. You see here PtCl4 minus negative, here PtH2O whole 4 plus. As the negative charge is decreasing and positive increasing, the inner chloride atoms are become more and more difficult to replace by H2O. As shown above, the complex become more and more positive, while the number of chloride ions in the complex diminishes and the consecutive detachment of the chloride ions become more and more difficult. Therefore, the relationship between this is K4 constant, K3, K2 and K1. So we can represent this relationship, that is relationship between K4 is greater than K3 is greater than K2 is greater than K1. Means here the replacement of chloride ion is more difficult. And hold between the stepwise dissociation constant equal to the product of all the steps step constants of the PtCl4 2 negative. Again, relationship between beta n and K1, K2 and up to Kn, the stepwise constant K1, K2 and up to Kn and overall formation constant, that is beta n, are related to one another from, for example, we can express that is beta 3 is equal to active mass of ml3. It is somewhat 3 should be in bottom side 3, and divide by this active mass of m into 3 ligands are there. On multiplying number numerator and denominator of above equation, we can get the total overall, the sum, that is beta n is equal to 1 and up to Kn. We get, since log K is directly proportional to the free energy of the reaction, that is delta G is equal to minus 2.303 RT log K, or delta G is equal to minus 2.303 RT log beta. From this, it is evident that overall stability constant beta n is equal to the product of the successive stepwise stability constant, that is K1, K2 and up to Kn. Next topic, that is kinetic versus thermodynamic stability. The term labile and inert show the speed or rate of at which the substitution of one ligand by other occurs. These terms represent the kinetic stability of complexes and should not be confused with the stable and unstable and stable respectively. Although thermodynamically stable complexes may be labile or inert, and unstable complexes, which are usually may be labile or may be inert. There is no correlation between the thermodynamic and kinetic stability terms. For example, Hg CN4 CN whole 4, that is tetracyanomercurate second, which is thermodynamically very stable. Formation constant is up to 10 to the power 42, but in fact it is labile. Since the solution it exchanges cyanide ligands with level cyanide ions, carbon 14, isotope 14, at very fast rate, like this reaction representing this one. Thus, stability of complex does not ensure its inertness. On the other hand, the complex CONH3 6, that is hexamine cobaltate, cobalt, which is thermodynamically unstable and can remain unchanged in acidic solution, as we already discussed this point earlier. Thus, this complex is unstable but inert in acidic solution. The stability of complex depends on the reaction energy, while liability of a compound depends on the activation energy. Larger the activation energy, lower will be the liability of the compound. That is, the complex will larger activation energy will react slowly. Now, next topic is factor affecting the stability of metal complexes. That is, many physical and chemical factors affect the formation and stability of complexes and coordination compounds. Some of them are the factors: environmental factors, that is temperature and pressure. Number 2, concentration factors. Number 3, nature of central metal ion. Number 4, nature of coordinating group or ligands. Number 5, nature of the ions outside the coordination sphere. Number 6, ring formation. Next, last, that is applicability of effective atomic number or atomic number rule. So, first of all, we will discuss these factors one by one. And the environmental factor, that is, environmental factor cover the temperature and pressure. Effect of temperature, as volatile coordinating groups such as H2O, NH3, ethyl diamine makes the compound less stable at elevated temperature. Such compounds decompose when heated. For example, this is a complex of chromium. When it heat and given temperature, it decompose and convert into in this compound. Next, here the effect of temperature, pressure. When the pressure above the compound is reduced, the volatile compound is lost. That is, hydrated metal complexes are readily dehydrated at low pressure. Next point is concentration factor. Complex of type CuCl4, that is tetrachlorocuprate, exists in solid state and its color is yellow in color. When dissolved in water, the characteristic pale blue hydrated copper second ions appears. That is, it indicates that this CuH2O whole 4 plus 4 chloride ions, this form tetrachlorocuprate second ion. This is yellow in color, but in fact, when we mix this compound with water or medium is H2O, these chloride ions are replaced by H2O and it gives color of blue color, pale blue color, hydrated copper second ion. Similarly, pink hydrated cobalt second ion is converted into aqueous solution blue complexes, two blue complexes by addition of chloride, but when diluted, the hydrated ion is regenerated. Means this is the impacts of dilution. Next point is here, nature of central metal ion. This factor is very important. The transition metals form most stable complexes. Number one, by which size of central metal ion. In general, the stability of complexes decrease with the increase of the size of the central metal ion complexes. Number two, thus the stability of complexes belonging to the same group decrease with the increase of size of the central metal ion, that is stability of the complex of the ions between Mn plus 2 and zinc plus 2 with a given ligand in order, that is order of stability. These all are divalent ions. Mn and is less than Fe plus 2. This cobalt is less than, this Fe is greater than Mn, this cobalt is greater than Fe plus 2, this nickel is greater than cobalt, and copper is greater than this nickel, but this zinc is less than copper. And you see its ionic radius. Ionic radius of Mn plus 2 is 0.91, Fe plus 2 is 0.83. These values are decreasing up to copper, and again it is increasing, that is zinc is 0.74. You see here the zinc plus 2 is also less stable than this Cu plus 2. This order of stability is also called natural order or Irving-Williams order of stability of complexes of plus 2 ions. Metal ions having charge density of the stable complexes, that is charge density is equal to charge over radius. If the value is more, compound or complex will be more stable. From we can also observe from these examples, that is charge of the central metal ion. Highly charged ions allow closer and faster approach, and greater force of attraction results into a stable complex. When the metal exists in two different oxidation states, the effect of charge and size are interrelated. For example, the size of Fe plus 2 is not very different from Fe plus 3, but Fe plus 3 carries higher charge than Fe plus 2. The charge density of Fe plus 3 being greater than that of Fe plus 2. Therefore, the complexes of Fe plus 3 are more stable than those of Fe plus 2 ions. As seen here, Fe plus 2, plus 3, these are cyanide ions. It is forming FeCN whole 6, and here 3 negative charge, where log beta, that is stability constant, is near about 31, which indicate this complex is quite stable or very stable. But in our case, when metal ion is divalent, that is plus 2, when these ligands are attaching, it is forming FeCN6, where minus 4 charge is there. Log beta is 8.3. It is quite low value rather than this previous one. So this compound will be log beta 8.3. It is less stable as compared with this FeCN6 plus minus 3. Thus, the stability of complex or complexes will the same ligand in order of, that is cobalt plus 3 will be greater than cobalt plus 2 ion. Similarly, these are the other ions which are will be less stable in this sequence. The electronegativity and polarizing power of the central metal ion. Electronegativity means the Bonding between the central metal ion and the ligand is due to the donation of electron pairs by the ligands. A strongly electron attracting central ion will give stable complexes. For example, complexes of Cu plus 2 and Cd plus 2 ions are more stable than those formed by sodium or sodium cation or calcium plus 2 ions respectively, because this is the fact that these are the bonding between the central metal ion and ligand donation of electron pair, because these atoms have the capacity to adjust those donated electrons their vacant d orbitals. Ionization energy of the central metal ion. In general, the stability of complexes given by divalent ions increase with the increase of the first and second ionization potential of the Mn plus 2 ions. Next point is nature of coordinating or group or the ligands. A highly charged and smaller ligand form more stable complexes. For example, the stability of complexes of given metal ions with halide ions, that is fluoride ion will be form more stable complexes rather than this chloride, bromide or iodide, or the their stability of the complexes will be in this order also. For neutral ligand say H2O or NH3, higher the dipole moment of smaller the size, the more stable of the complexes will be formed. The more basic is the ligand, more easily it can be donate electron pair to central metal ion, and hence it can form complexes of greater stability. Nature of ions outside the coordinating or coordination sphere, ions such as cyanide ion, thiocyanide, chloride, bromide, iodide, or Cr2O4 dichromate, exhibit tendencies of the entering the coordination sphere and thus affect the stabilities of coordination compounds. On the other hand, ions such as NO3 or Cl4 negative shows very little tendency. Next very important headings, that is ring or chelate formation. Ring or chelate means the chelation or complexation takes place. The chelated complexes are more stable than the non-chelated complexes. For example, as compare differences in the in thermodynamic quantities, that is ethylene diamine form a complex with nickel ions. You say this hydrated nickel ion, when it reacts with ethyl diamine, it form a this complex, and again another ligand replaced by this water form this Ni ethyl diamine, triethyl diamine complex ion, and as each of displaced to H2O, and the value of its delta S, that is entropy, is equal to R 55.5 or in sum that is plus 7.9 calorie per mole, that is extra H2O liberated, and some examples are here. These are the complexes, and these are the values of delta Finney energy. These are entropy, this is enthalpy, entropy. The value of delta Finney energy, that is negative, delta H enthalpy is also negative, but entropy is positive and almost higher one in this case. So delta G and delta H are negative, means heat is evolving and complex will be more and more stable. So by calculation from this equation, we can find out its free energy, or delta H, delta S are, that is gas constant, and this is temperature. As I already discussed earlier, that if delta G is negative or delta H is enthalpy, means heat evolve or change is also negative, and delta H is entropy change is positive or greater, then compound or complex will be more and more stable. Increased stability dominate by delta S, that is this entropy. As chillate effect is an entropic effect. Chillate effect is primarily due to the differences in reactions, entropies between the chillated and the non-chillated complexes in a dilute solution. This is a significant positive change in the entropy, and it makes delta G, free energy, negative for this reaction. The ethyl diamine molecule bonded to the copper in two places and form a ring structure which is more stable than similar to complex with unidentate ligand, because the dissociation of the chillated complex involving breaking of more than one bond. In simple complex there is only a single bond, but in chillation or in chillating effect, that is metal ion is coordinated by more than two groups. Applicability of the effective atomic number. The formation of stable mono and polynuclear metal carbonyl complexes follow the EAN, that is effective atomic number rule, which stated that the metal atom achieve a atomic number of the next noble gas by coordinating with the carbon monoxide, that is CO molecule. For example, nickel carbonyl NiCO4, atomic number of nickel is 28. It has 28 electron, and krypton, the next noble gas, contains 36 electrons. The 8 electrons needed by nickel to reach the next EAN 36, and these 8 electrons are supplied by 4 carbonyl group, 4 a pair of electrons means 8 electrons, and thus nickel forms a stable mononuclear tetracarbonyl complex or compound. This stability constant or stability of such complexes are utilized or applicable in analysis of basic radicals, particularly fourth group nickel, cobalt, and which are stable amines compounds are formed. But in third group element, that is aluminum, Fe, etc., are formed hydroxide of their metal ion. So we can easily separate out these third group from fourth group, and so many other applications are also there. Thank you very much.